Right, the start of the next topic, which is going back to your network. And from this, we are going to look at network, things like optimization, things like minimum distance, but using a different algorithms, using the Prim's algorithm and the Kruskal's algorithm. Sounds awful, but it's pretty straightforward. You just need to follow step by step. All right. Probably the slightly more difficult one is when we come to project network. That's about all. The rest are all pretty much, if you follow step by step, you should be able to work it out quite pretty straightforward, like I said. So we're going back to network again, and this time we're going to start off with tree. All right. The first thing we're going to look at is called a spanning tree, and it is just a quick revision of what you have learned in first semester. All right. So the objective of the day, what I want all of you to do is to be able to recall what a tree is. Then identifying a tree. Those two are actually from first semester. Now, then we will define a spanning tree. And it's actually just a subgraph of a graph which contains all the vertices, and it's a tree. All right? And then we should be able to construct a spanning tree from a given graph. Pretty straightforward, pretty much introduction. So if you recall, a tree is a graph which is connected with a unique path between every pair of vertices. All right, I've typed with a twice. All right, so it's just a graph with a unique path between every pair of vertices. It does not contain any loops, no multiple edges, does not contain any cycle or acyclic, and every edge is a bridge. The last sentence is important. A tree with n vertices will have n minus 1 edge. Now, just quickly, recall multi-edges. If I've got A, B, and C, if this is connected, there is no multiple edges because there's one edge from A to C, one edge from B to C, one edge from A to B. But if I've got A to C, two edges, that is considered as multiple edges. Alright? Now loops. This is a loop. V has a loop, it has an edge going back to itself. Alright? Any cycle. A, B, C is a cycle because you can go from A to B to C and back to A. Every edge is a bridge. So bridge, if you take away one of the edge, a bridge which causes the graph to be two separate graphs or to disconnect two graphs, then that's a bridge. So if I've got something like this, A, B, C, D, E, and okay. So DA is a bridge. If I take away DA, you've got two separate graphs. Alright? And disconnected. And if I take away DE, from one connected graph, it becomes a disconnected graph. Alright? So think about what a bridge is. So these loops from first semester, multiple edges, there's multiple edges, cycle, and also a bridge. Alright? So now, let's have a look at what a tree is. These are trees. Alright? This is not a tree because there's a cycle. This is not a tree because it's not connected. This again, there's a cycle, therefore it is not a tree. So a tree, basically, you've got one edge, a unique path only between the vertices. Alright? You cannot connect a unique path as in from, say, A to B, A to C. There's no path connecting there. There's only one way of going up and down. That's right, A, C, and B, or some. Or you need to go from here to here. There's only one unique path connecting them. All right. There's no loop. There's no cycle, and that's nothing that's not connected. All right. Now, from here, you should be able to identify which one is a tree. Looking at that, what you need to see, the first thing is whether there's any loops. If there's a loop, that is not a tree. Correct? Is there any cycle? That one, it's not a tree. There's multiple edges, also a cycle, so that's not a tree. So this tree, oh, this is disconnected, therefore it's not a tree. Whereas this one unique path and one unique path. So therefore those two are trees. All right? Oops. So that's loop. Let me write it down. Disconnected. Cycle and multiple edges. So they are not trees, not trees, not trees, not trees. Where's those two? They are trees. Pretty straightforward to identify a tree. All right. Now, a spanning tree. This is a definition of a spanning tree which you should know. I will give you a copy of all the vocabulary you need to know tomorrow. All right. A spanning tree of connected graph is a subgraph which includes all vertices and it is a tree. All right. So what you need to do is think about an original graph. For example, this one. I can take away some of the edges. However, a spanning tree requires you to have all vertices connected, and it has to be a tree. So for example, this is a subgraph, this one here. It is not a tree because there is a cycle, right? So that is not a tree. Is this a tree? No, there is a cycle, so therefore it is not a tree. There are four trees here, the four subgraphs which can be spanning tree, which is this, and this. Alright? You must be able to identify what a tree is and a spanning tree from a subgraph. Alright? So those four are spanning trees. These two, there is a cycle, there's a cycle, so it's not a spanning tree. Now, to construct a spanning tree of a graph, it must have no cycle, one edge less than the number of vertices. So I've got four vertices. So what do I need? I need only three edges, correct? Says that one edge less than the number of vertices. If I've got four, in this case, four vertices, I can construct a subgraph, and it will be a spanning tree, and it must have one edge less than the number of vertices. And make sure that there's no cycle, no loop. So constructing, I can try with that. Is that a tree? Yeah? Can you actually try a few, draw a few, and see how many you can come up with? I have seen exam question like this, asking you to actually draw as many spanning tree as you can from a graph. So remember, no cycle, no loops, one edge less than the number of vertices. And it has to be a tree.
What's the minimum number of vertices? Three?
The number of edges is always one, for a spanning tree is always one less than the vertices.
Yeah, but what's the minimum number of vertices you can have? You have two?
Yep, two is a tree. Yep,
That's a tree.
there's a tree, two is a tree.
Three vertices and two edges, that's a tree?
Yes, that's correct.
Yeah, okay.
However, for spanning tree in this case, you must have all the vertices in there, the subgraph of all the vertices. All right? You need a subgraph of all the vertices. So if you have tried it, this is what I've got. These are all the subgraph from the original graph, and they are all spanning trees. See how I did that? First thing I did was I took away the diagonal. So I'm left with sort of like a rectangle. Then I took each one of the rectangle out, one each out. Then what I did is I kept the diagonal there, took two out. Could be these two, could be these two, and could be that, could be whatever, those two. All right. See how I did it? I did it systematically. All right. So this connected graph has 8 spanning trees. That's it. That's basically the lesson today. Pretty straightforward. You just need to recall what a tree is. You need to identify a tree, and you should be able to construct a spanning tree from a given graph. So you should have about 25 minutes to finish exercise 5A.